Alright, so to cope with failing the FELs I made this year, I'm gonna go over a bunch of problems from like this Everest book. It's like I think it's called Physics Mechanics by Everest. Yeah, so let's go. So this is a first problem in the book. So it's 1.1. So the problem is a ball is dropped. So here's a ball. It got dropped. And then another ball is dropped from the same spot a second later. So then what happens? There's another ball and it got dropped. And this is going to be ball one. Here, this is ball one and this is ball two. So as time goes on, we want to find uh, the distance between them. So we want to find the relationship between the distances, and in order to do that, we just have to we have to look at their positions, right? So what is position formula? For a falling object, it's y equals to negative 1/2 gt squared. So I'm actually gonna go over the derivation for this formula because I think it's pretty neat. So yeah, also I do kind of expect like some type of prerequisite in physics. But yeah, this is like the derivation. So this is how I would derive it pretty quickly. There's definitely other ways to derive it. Yeah, so we're gonna start with this equation, like the definition of acceleration. And then we're gonna move this t over there. So a t equals to vf minus vo. And then we're gonna get vf equals to vo plus at. So this is the first out of the kinematic equations. And then essentially what we do from here is we need to know like a little calculus. So we're gonna need to know that dx equals dt equals dx over dt equals v. So we move it over here and then we take the integral of both sides. And we get that delta x equals to the integral of v dt. Yeah. So essentially, what we do here is we put that in there. We put the entire equation inside the integral. So, how do I move this? I can use hand. We put the entire equation in the integral. So delta x equals to um, yeah, vo, the integral of vo plus a t with respect to dt. So this one, this term, remember the integral for sum, the sum, what is it? I think you just sum it, right? Yeah, you just it's like the derivative, right? The sum of the derivative of the sum is some derivative. It's like the opposite. Yeah. So delta x equals v o t plus 1/2 a t squared. So for this term, it didn't have a t. So we gave it a t. And for this term, the a is constant. And when we do like kinematics for like FMO or something like that, it's constant. The only like the case where it wouldn't be constant would be like air resistance. But then we're going to like ordinary differential equations and like guessing solutions, and that's not a very fun time for us. So yeah. So I think if you just take the a as a constant, so it's out of the integral, and then t dt, and then like what's the integral of x dx? Oh yeah, it's kind of like that type of question. So it's d over 2. So yeah, that's how we got this equation. And when we drop the ball, the v initial is 0. So it's 0. And I know I use x for this. This isn't, it's not like specific to the x direction. It can also be like y direction. So let's rewrite it like that. So the VO is 0. And in the y axis, a equals negative g. The acceleration of the ball is negative g, the negative gravity. So negative 9.8, but we're going to say it's 10. So yeah, this is how we got the equation. See, I'm so smart. I could derivate things too. So yeah, so this is how we got this equation. And yeah, let's go back to the question now that we have the knowledge. So essentially what we do here is we need to use that same equation we just got to solve the question. So we need to track the position of each ball, is what I'm saying. So for the first ball, y1 equals to negative 1 half gt squared. That makes sense, right? Now this one is like kind of different. 1 half g. And instead of just putting t, we're going to do t minus 1. And the reason why we do this is because it's 1 second later. 1 second later, so it's minus 1. Yeah, so let's say we had this term. Let's say this is for the time for the second ball, t minus 1. If we added 1, right? If we added 1, then it'll just become t. So it'll become t. So you can see that the relationship still holds. I hope that was like a good way to explain it. I was also kind of confused when I first learned this. Yeah. So we have these two equations, and now there's two ways to solve this. So either you can recognize that if I create an equation where like subtract them, or I do like y minus y2, um, you'll see it's like the quadratic, right? The quadratic, it's gonna give you d. Is what I'm saying, right? It's gonna give you d because like a quadratic is gonna keep like going up. Yeah, but like the second way to do this, or like or what I did when I first solved this question, is I literally just plugged in numbers. So like I was like t equals to 1, t equals to 2, and t equals to 3, and we're gonna put our equation back up there. Negative 1 half g, we're gonna say g equals to 10, so negative 5t squared. So for y1, we got negative 5. And for y2, we got 0. And for y1, we got negative 20. And for y2, remember it's t minus 1. I need to put that back up there. Squared. It's going to be negative 5. And for this one, oh. And for this one, y1 equals to, what is that? Negative 5 times 9 equals negative 45. And y2 equals to negative 20. And you can just see, like, it's like this relationship. Like, you can see it's the same because it's just lagging behind 1. So you can see, like, this is like, what, a change in like 25. This is a change in 15. This is a change in 5. So yeah, it's D. It's D. That's how I got the answer, and that's like the full explanation. Yeah, so I hope you enjoyed the video. Yeah.